research in Austin made a project about software transactional memory, and one of the results was a paper with the title "Software Transactional Memory, Why is it only a research toy?" And they observed several things, and some are reported here, such as for each shared access there will be tens of additional machine instructions executed for the logging and the checking, and that can be really expensive. We don't want to waste that many extra instructions. Ideally, there should be no extra instructions, and that is possible for hardware transactional memory, but not for software transactional memory. Both need extra instructions, or extra clock cycles at least, when we set up and commit a transaction. Okay, but when doing the accesses in a transaction, there shouldn't be overhead, at least not too much. Okay, another problem is that if the transactions observe an object and then that object is deallocated and the memory is reallocated for another object, how can the transactional memory system know that they are different objects? It's just the different addresses that they check. Okay, the program may contain libraries and or other software that is not aware of transactions, and then these transactions may have to be executed in sequence or serialized in order to avoid triggering of conflicts and restarting of transactions. And another thing is, and I will come back to that, debugging can be more complicated. And the reason is that it is more non-deterministic which transaction will be succeed or which one will be restarted. So this is not the ultimate solution to easy, efficient parallel programming. There are details which complicate life. So, hardware transactional memory then. Again, it's software which defines the transactions. I mean the programmer, obviously. And the hardware writes to some kind of buffer locally. And this could be an on-chip buffer of a few kilobytes, or it could be larger. And if this buffer is not sufficient, there can be different actions taken, such as moving the data to raw memory. That obviously will take time. When the transaction is completed, meaning we execute the special instruction, then the hardware makes the writes visible to other threads. Okay, and when this happens, the other threads can observe which data is being committed and then detect that they have created a conflict and restart themselves, for instance. Okay, so the granularity of checking for conflicts, it's not one machine word. It's instead a cache block. Recall, a cache block can be 32 or 64 or perhaps 128 bytes. And that means we can be unlucky, namely that one transaction reads or writes one part of this cache block, and another transaction another part of the cache block, and there is really no conflict, but due to these variables that were modified and read, by different transactions happens to be in the same cache block, the transactional memory system can think that there is a conflict. So this is related to false sharing, which I will talk about more in lecture 9. So how can we optimize performance for transactional memory? Well, the obvious thing is that we should not write or create transactions that access too much shared data. And it's mostly because we want to avoid conflicts. And it's also that the buffer where the local writes are done could overflow, which results in overhead. But making too small transactions also creates overhead. Okay,